Welcome back to the deep dive. Today, we're zeroing in on something that seems pretty specific, maybe even a little mundane on the surface, but it's actually crucial.
It really is. We're talking about a piece of hardware that solves a very specific, very important problem.
We are. It's the NTI PWR-24V-5V2A external power converter. And our mission today is to dig into the specs and understand what elevates this little box into something essential for system resilience.
Exactly. I mean, when you're managing specialized communication infrastructure, reliability is everything. It all comes down to the details.
Little things.
Yeah. Understanding the tolerances of one component like this, well, it gives you a much broader insight into how the entire system is designed to survive.
So let's start with the absolute basics. What does this thing actually do?
At its core, it's a DC to DC converter. It takes a 24-volt DC source.
And just steps it down.
Right. It takes that input and delivers a really clean, stable positive 5 volts, and it's capable of handling a 2-amp load.
But the input, it's not strictly 24 volts, is it? There's some flexibility there.
A lot of flexibility. It will accept anything from 18 volts all the way up to 36 volts DC.
And that wide range, that's the first big clue about its real purpose, right?
It's the first signal, yeah.
Yeah.
It's designed to absorb power fluctuations you'd find in industrial or telecom environments. That's where it's meant to live.
Okay, let's unpack this. So thinking about those conditions, the input connection itself must be pretty important.
It is. It's not some flimsy barrel jack. It uses a 3-pole detachable screw terminal.
Which screams industrial. It's about a secure, permanent connection, not plug-and-play convenience.
And you absolutely need that security. But here's what's fascinating. The one design choice that really simplifies installation and honestly prevents failure.
What's that?
The converter accepts positive or negative polarity on the input.
Oh, wow. Okay, hold on. That's a huge
This
feature.
is a game changer in the field.
So you're saying an installer could accidentally reverse the wires, which has to be a common mistake.
A very common mistake, especially on older systems.
And it doesn't fry the unit.
Yeah,
It just works.
It just works. It automatically adapts. That single feature is a critical safeguard. It prevents catastrophic failure right at deployment.
That's incredible. Okay, so that covers electrical resilience. But shifting gears a bit, this device has to physically survive, too. It's not always going into a nice air-conditioned server room.
No, definitely not. And that brings up the next critical spec.
How extreme can the operational environment actually be for this thing?
The operating temperature range is, well, it's properly industrial. We're talking from a freezing -13 degrees all the way up to 158 degrees Fahrenheit.
Wow. So that's, what, -25 to 70 Celsius?
Exactly. That rating means it's built for those non-climate controlled shelters, outdoor equipment racks, places where temperatures can swing wildly. It's designed not to be the point of failure.
And I see it also has the regulatory approvals you'd expect. RoHS, TAA compliant.
Which is important context. RoHS is about restricting hazardous materials, and TAA compliance means it can be used in, for example, U.S. government projects. It's all part of being a serious piece of infrastructure.
So if we put this all together, the NTI PWR-24V-5V2A is really this hyper-specialized, incredibly resilient bridge.
That's a good way to put it. It's a bridge to neutralize the risks of connecting sensitive 5-volt equipment to often volatile 24-volt industrial systems.
It's all about risk mitigation.
It is. And remember, while we focused on this 24 to 5-volt unit, this is a whole category of device. The same manufacturer makes converters for 48-volt systems, which is another huge telecom standard, stepping it down to 5 or 12 volts.
So there's a whole ecosystem of these solutions.
There is. And for something to think about after this, consider for a moment why some major communication infrastructures globally adopted negative DC power in the first place. What historical or environmental factors would lead to a design choice that requires a device like this to be polarity agnostic? It's a fascinating bit of engineering history.